Everyone thinks CoWoS is the endgame of AI chip packaging. It isn't. The next leap in AI performance won't come from printing smaller transistors, and it won't come from a bigger interposer either. It comes from something stranger, taking two finished chips and fusing them into one. Copper to copper, atom to atom, no solder at all. It's called hybrid bonding. TSMC needs it. Samsung is betting its HBM4 comeback on it, and one quiet Dutch company already builds the machines everyone will have to buy. This is the technology that comes after CoWoS. For 50 years, making chips faster meant making transistors smaller. That race isn't over, but every step now costs billions and buys less. So the industry opened a second front. Packaging, connecting chips together so tightly that they behave like one giant chip. That's the story of CoWoS, the packaging platform behind nearly every AI accelerator shipping today. But look closely inside a CoWoS package, and you'll find something surprisingly old holding it together. Solder bumps, tiny balls of metal, tens of microns wide, spaced so far apart that most of the silicon's edge is wasted. Every bump adds distance. Distance adds delay, resistance, and heat. The bumps have become the bottleneck. Hybrid bonding's answer is radical. Delete them entirely. And deleting them quietly changes who wins the next round of the AI hardware war. Here's what hybrid bonding actually does. Take two wafers, or a die and a wafer. Polish their surfaces until they are flat at the atomic scale. Roughness is measured in fractions of a nanometer. Each surface carries copper pads embedded in an insulating dielectric. Press the two surfaces together at room temperature and the dielectric bonds on contact. Then heat the pair a few hundred degrees. The copper pads expand, touch, and fuse into continuous metal. No solder, no underfill, no gap. Electrically, two chips become one. The numbers are hard to overstate. Solder microbumps sit 40 to 50 microns apart. Hybrid bond pads sit below 10 microns. In the lab, below 1. That's a leap of 100 to 1,000 times more connections in the same area. Signals travel micrometers instead of hundreds of micrometers, so they arrive faster and burn far less power. And this is not a laboratory curiosity. If you own a PC with AMD's X3D gaming processors, you already own hybrid bonding. The stacked cache on those chips is fused this way, using TSMC's SoIC process, and it has shipped in volume for years. The technology works. The question has always been scale. The scale arrives with HBM, high bandwidth memory, the DRAM towers feeding every AI GPU. Today, those towers are stacked with microbumps, and in SK hynix's case, a molding technique called MR-MUF that quietly won the HBM3 era. But the roadmap ahead is brutal. HBM4 wants more layers, 12, 16, eventually 20, inside a package height that barely grows. Microbumps add height with every layer, and the mold compound that binds the stack struggles as the gaps shrink toward zero. At 16 layers, much of the industry believes, the old toolkit simply runs out of road. Hybrid bonding removes the bumps, so each additional DRAM layer costs almost no additional height. Better still, heat escapes the stack through solid copper instead of mold compound. And heat is the silent killer of stacked memory. This spring, SK hynix validated a 12-layer hybrid-bonded HBM stack and is now working to push production yields up. Samsung, having lost the last round, is skipping the incremental step entirely, betting its HBM4 line directly on hybrid bonding, a leapfrog attempt on the incumbent. Analysts now expect hybrid bonding to reach roughly half of the advanced stacking market within a few years. When memory flips, the tool market flips with it. So who builds the machines? Follow the precision requirement. To fuse copper pads a few microns wide, a bonder has to place a die with an accuracy measured in single-digit nanometers, while keeping the surfaces so clean that a single stray particle ruins the bond. Very few companies on Earth can do this at production speed. The company that got there first is BE Semiconductor Industries, BSI, a Dutch equipment maker most people have never heard of. BSI spent a decade developing hybrid bonders and partnered with Applied Materials to pair its die placement tools with Applied's wafer preparation steps. Today, its machines sit inside the pilot lines and production lines of the leading foundry and the leading memory makers. The financial curve tells the story better than any roadmap. 3 years ago, hybrid bonding was a rounding error in BESI's accounts, a few tens of millions of euros. This year, it approaches $500 million, roughly a third of the company's entire revenue. The market for these bonders is projected to keep multiplying as HBM4 ramps. It's the oldest pattern in this industry. When everyone digs for gold, the surest business is selling shovels. BSI sells the only shovel that works at 10 nanometers. But before anyone declares a monopoly, look at the counterweights, because this is not ASML, and the race is far from settled. First, competition is real. ASMPT, a major packaging equipment maker, is shipping its own hybrid bonders. In Korea, tool makers like Hanmi Semiconductor, the company behind SK hynix's HBM stacking lines, are racing to extend into next-generation bonders, with the home team advantage of sitting next door to the memory giants. In wafer-to-wafer bonding, Austria's EV Group is already the quiet standard. Second, the economics still favor the old way. For now, MR-MUF is cheaper, its yields are proven, and SK hynix insists it has road left. Hybrid bonding demands cleanroom-grade purity at the assembly step, and it is unforgiving. Fuse one bad die onto a stack, and there is no rework. The solder era allowed second chances. The fused era does not. Third, timing can slip. Full adoption may wait for 16-layer stacks. And the B memory makers will delay that transition as long as economics allow. Equipment orders are cyclical, and a 1-year slip hits a toolmaker's revenue hard. The direction is not in question. The calendar very much is. So here's the industry view, 3 layers deep. At the top, TSMC extends its moat. Hybrid bonding is not a threat to CoWoS, it's the sequel. SoIC stacks chips vertically, CoWoS spreads them horizontally, and TSMC sells the combination as a package deal. Literally. The more bonding matters, the harder it becomes to leave the leading foundry. In the middle, the memory race resets. Samsung's decision to leapfrog straight to hybrid bonding on HBM4 is the boldest bet in memory today. If it lands, the HBM leaderboard reshuffles for the first time in years. If yields disappoint, SK hynix is patient, incremental path wins again. Either way, the transition is the moment of maximum danger for the incumbent and maximum opportunity for the challenger. And underneath both sits the machine layer. Whoever wins the memory war, they will fight it with bonders. And today, the clear leader in die-to-wafer hybrid bonding is BESI, with rivals closing but behind. The honest caveats: it is not a true monopoly. The timing can slip a year, and the market has noticed. This is no undiscovered stock. But structurally, the pattern holds. In a war over fusing chips, the company selling the fusing machines doesn't need to pick a side. This video is the second chapter of a story that began with CoWoS, the packaging technology that carried AI accelerators this far. If you haven't seen that explainer, it's linked on screen and in the description. The 2 videos are designed to be watched together. This channel is the anonymous semiconductor industry view. No hype, no cheerleading, just how the supply chain actually works and who quietly profits from it. If that's the kind of analysis you want more of, subscribe and turn on notifications. Thanks for watching.